Top 10 mind-bending facts about black holes, table of contents 1. You can't see a black hole, only its ghostly shadow. 2. The event horizon is a waterfall in spacetime 3. You wouldn't be crushed, you'd be spaghettified. 4. Time warps, so much that you could watch the universe. Die 5. The singularity is a point where physics breaks 6. They come in supermassive sizes that shouldn't exist. 7. Black holes are not cosmic vacuum cleaners. 8. They can spin so fast, they drag space-time with them. 9. Black holes aren't forever. They evaporate. 10. They are the parents of new stars and galaxies. Conclusion. Further reading. Look up at the night sky. Among the glittering stars and distant galaxies lie the universe's most perfect and most terrifying monsters. They are the ultimate cosmic enigmas, objects that defy our everyday intuition and push the laws of physics to their absolute breaking point. We're talking, of course, about black holes. A black hole is often described as a region of space-time where gravity is so overwhelmingly strong that nothing, not even light, the fastest thing in the universe, can escape. But that simple definition barely scratches the surface of their strangeness. They are not just cosmic vacuum cleaners. They are paradoxes made real. They are time machines, gateways to infinity, and laboratories for theories we can't yet prove. If you've ever felt your mind stretch while pondering the universe, prepare for it to snap. We're moving beyond the simple, they're heavy and dark facts. We're diving deep into the 10 most truly mind-bending realities of black holes, exploring the concepts that make them the most fascinating objects in all of creation. 1. You can't see a black hole, only its ghostly shadow. This sounds obvious, right? No light escapes, so they're black. But the mind-bending part is how we find something that is, by its very nature, invisible. We can't see the black hole itself, but we can see the chaos it wreaks on its surroundings. Imagine a perfectly invisible drain in a bathtub. You can't see the hole, but you can see the water swirling frantically around it, accelerating as it gets closer and vanishing at a single point. Astronomers find black holes in the same way. We look for their shadow cast against the universe. This can happen in a few ways. Accretion disks. As gas, dust, and an unlucky star get pulled toward a black hole, they don't fall straight in. They spiral, forming a massive flat disk called an accretion disk. The friction and intense gravitational forces in this disk heat the material to billions of degrees, causing it to shine brighter than an entire galaxy in high-energy X-rays. We see this blazing, doomed ring of light with a perfect black shadow in the middle, the event horizon. Gravitational lensing. Einstein's general relativity tells us that massive objects warp the fabric of space-time. A black hole's immense gravity creates such a profound dip that light from a different, distant galaxy passing nearby will be bent and distorted, like looking through the base of a wine glass. This gravitational lensing effect can create strange arcs or even multiple images of the same galaxy, revealing the invisible object's presence. Stellar orbits. We can observe stars orbiting nothing. At the center of our own Milky Way, astronomers have tracked stars moving at mind-boggling speeds, whipping around an empty point in space. By calculating their orbits, we can determine that the nothing they're orbiting has the mass of 4 million suns. That, we know, is the supermassive black hole Sagittarius A2. The event horizon is a waterfall in spacetime. Every black hole has a point of no return called the event horizon. This is not a physical surface. You wouldn't bang your head on it. It is an information boundary, a one-way door in the universe. The mind-bending part is what defines this boundary. Think of it this way. To escape Earth's gravity, you need to travel at 25,000 miles per hour, about 11.2 kilometers per second, our escape velocity. For a black hole, the escape velocity increases the closer you get. The event horizon is the precise distance from the center, the singularity, where the escape velocity becomes equal to the speed of light. Since nothing in the universe can travel faster than light, anything that crosses this line is trapped forever. A brilliant analogy is a person in a rowboat on a river that leads to a giant waterfall. Far upstream, they can easily paddle back to shore. As they drift, the current gets stronger. They reach a point where the water is flowing at the exact maximum speed they can paddle. They can row as hard as they want, but they only stay in the same place. This is the event horizon. If they drift 1 inch further, the current becomes faster than their maximum speed, and they are inevitably pulled over the edge. In a black hole, the current is space-time itself, flowing into the singularity faster than light. Once you cross that horizon, all paths in your future, all possible directions in space-time, point only toward the center. There is no out. 3. You wouldn't be crushed, you'd be spaghettified. So what does happen if you fall into a black hole? The reality is far stranger and more gruesome than simply being crushed. The process is called spaghettification, and it's a direct consequence of tidal forces. We experience tidal forces on Earth from the moon. The moon's gravity pulls slightly stronger on the side of Earth facing it, creating a high tide, and slightly weaker on the side facing away, leaving another high tide. The difference in gravity across the planet is the tidal force. Now let's apply this to a black hole, where the gravitational gradient is almost infinitely steep. Imagine you are falling feet first toward the black hole. As you get close, the gravity at your feet will be billions of times stronger than the gravity at your head. The black hole will pull on your feet with so much more force than your head that you will be stretched, and stretched, and stretched. This tidal force would pull you apart, atom by atom, stretching your body into a long, thin stream of subatomic particles, like a strand of spaghetti, before you ever even reach the center. For a smaller stellar mass black hole, this spaghettification would happen before you even cross the event horizon. For a supermassive black hole, like the one in Interstellar, the gravity gradient is gentler at the horizon, so you could, in theory, cross the event horizon completely intact, only to be spaghettified much later on your journey to the center. 4. Time warps. So much that you could watch the universe die. This is where Einstein's general relativity gets truly bizarre. One of its key predictions is gravitational time dilation. In simple terms, stronger gravity makes time pass more slowly. This isn't a theory, it's a proven fact. The GPS satellites orbiting Earth are in slightly weaker gravity than we are on the surface. Because of this, their internal clocks run faster than clocks on the ground, by about 38 microseconds per day. If we didn't correct for this relativistic effect, your GPS would be off by miles within a day. A black hole is the most extreme example. Its gravity is so intense that time stretches to a near standstill. Let's do a thought experiment. You are in a spaceship, safely orbiting far from a black hole. Your friend in a separate ship decides to fall in. You watch them through a telescope. As they approach the event horizon, you would see their clock and all their actions slow down. They would seem to move in extreme slow motion. As they got closer and closer to the edge, their image would appear to slow down further and further, red shifting as the light waves lose energy climbing out of the gravity well. You would see them freeze at the event horizon, their image stuck in time, fading over billions of years. You would never see them cross. From your friend's perspective, however, their own clock ticks normally. They would cross the event horizon without any sense of slowing down, ignoring spaghettification. But looking back out at you, they would see your clock and the clock of the entire universe speeding up. They would see stars born and die, galaxies merge, and perhaps in their final moments, witness the entire future history of the universe flash before their eyes. 5. The singularity is a point where physics breaks. We've talked about what happens at the event horizon, but what's inside? What is at the very heart of a black hole? The answer is a singularity. Our current understanding, based on Einstein's general relativity, says that all the mass that falls into a black hole, entire stars, gas clouds, light itself, gets crushed down to a point of zero volume and infinite density. Let that sink in. It's not extremely small, it's infinitely small. It's as if you took the mass of 1,000,000 suns and packed it into a space smaller than a single atom. This is the point where our math and our physics simply stop working. You can't divide by zero, and in a singularity, the laws of physics are forced to do just that. Space-time curvature becomes infinite. Density becomes infinite. It's a break in the fabric of reality itself. This is the holy grail for modern physicists. General relativity, our law for gravity in the big, and quantum mechanics, our law for the small, are the two pillars of 20th century science. But they famously don't work together. In a singularity, the big, immense gravity, and the small, a subatomic point, are forced to coexist. To understand what a singularity really is, we will need a new theory of everything, like string theory or loop quantum gravity, that finally unifies these two great ideas. 6. They come in supermassive sizes that shouldn't exist. We typically think of black holes forming when a single massive star dies in a supernova. This creates a stellar mass black hole, perhaps 5 to 100 times the mass of our sun. But the universe also creates supermassive black holes. These are the leviathans. They are millions to billions of times the mass of our sun. And we've discovered that nearly every large galaxy, including our own Milky Way, has one of these giants lurking at its core. The truly mind-bending part is their origin. How do you make something so big? Stellar black holes are like puddles, but supermassive black holes are like oceans. How do these oceans form? We have a few theories, but none are complete. Did giant primordial clouds of gas in the early universe collapse directly into massive black holes, skipping the star phase? Did stellar black holes form and then merge over and over? The problem is one of time. We've seen supermassive black holes in the very early universe, existing when the cosmos was just a fraction of its current age. There doesn't seem to have been enough time for them to grow so big, so fast, by eating stars or merging. Their very existence challenges our models of galaxy formation and cosmic evolution. 7. Black holes are not cosmic vacuum cleaners. This is one of the biggest misconceptions in all of astronomy. Black holes do not suck things in from across the galaxy. Their gravity is powerful, but it's not magical. Here's a simple fact. From a distance, a black hole's gravity is exactly the same as any other object of the same mass. Let's try a thought experiment. If our sun were to magically and instantly be replaced by a black hole of the exact same mass, about one solar mass, what would happen to Earth? Absolutely nothing. Well, aside from us freezing to death in darkness. Earth would not get sucked in. It would continue to orbit the black hole in the exact same path, at the exact same speed, for the rest of time. The gravitational pull we feel depends on two things: mass and distance. Since the black hole's mass is the same as the sun's, and our distance is the same, the gravity we'd feel is identical. A black hole is only dangerous when you get very close to its event horizon, a region that is, for a sun-sized black hole, only a few miles across. You have to be practically on a direct collision course with that tiny spot to be captured. The rest of the solar system would be blissfully unaware. 8. They can spin so fast they drag space-time with them. When a massive spinning star collapses, it doesn't just lose its mass, it has to conserve its spin, or angular momentum. Think of an ice skater. They start a spin with their arms outstretched and then pull their arms in, causing them to spin dramatically faster. Now imagine a star billions of miles wide, spinning perhaps once a month, collapsing into a singularity only a few miles wide. The resulting spin speed is almost unimaginable, with the event horizon spinning at near the speed of light. These are called Kerr black holes, and they are even weirder than their non-spinning counterparts. A spinning black hole's gravity is so extreme that it twists the fabric of space-time around it. This frame-dragging effect creates a region outside the event horizon called the ergosphere. Inside the ergosphere, space-time itself is being dragged around the black hole faster than the speed of light. This means an object cannot stay still, any more than you can stay still in a tornado. You are forced to spin with the black hole. The bizarre part? You can, in theory, enter the ergosphere and still escape, as long as you stay outside the event horizon. This led to a famous thought experiment by Roger Penrose, who calculated that a sufficiently advanced civilization could steal energy from a spinning black hole by dropping an object into the ergosphere and letting it split in two, with one half falling in and the other escaping with more energy than it started with. 9. Black holes aren't forever. They evaporate. For decades, black holes were thought to be truly black and permanent, the universe's final prisons. Then, in 1974, Stephen Hawking combined general relativity with quantum mechanics and came to a revolutionary conclusion: black holes must glow. This glow is called Hawking radiation. The concept is one of the most brilliant and difficult in physics. In quantum field theory, empty space is not empty at all. It's a roiling, fizzing quantum foam of virtual particles. Particle-antiparticle pairs, like an electron and a positron, are constantly popping into existence and then annihilating each other in a tiny fraction of a second, borrowing energy from the vacuum before paying it back. Hawking realized that if this particle pair production happens right at the edge of an event horizon, a strange thing can occur. It's possible for one particle, say the antiparticle, to fall into the black hole, while the other particle, the electron, escapes. Because the antiparticle fell in, the electron can no longer annihilate. It becomes a real particle and flies off into space. To an outside observer, it looks like the black hole has just emitted a particle. But energy cannot be created from nothing. The energy to make that escaping particle real has to come from somewhere. It comes from the black hole's own mass energy. The particle that fell in actually had negative energy relative to the outside universe, which when added to the black hole, reduces its total mass. The result? Over truly vast timescales, the black hole slowly loses mass, particle by particle. It evaporates. For a stellar mass black hole, this process takes an incomprehensible 10 to the 67th power years. But given enough time, far, far longer than the current age of the universe, every black hole will eventually shrink, get hotter and hotter, and finally explode in a final, brilliant flash of gamma rays. 10. They are the parents of new stars and galaxies. We've painted a picture of black holes as cosmic destroyers. They stretch, they trap, they consume. But the modern view of cosmology is shifting. Black holes aren't just endings, they are also beginnings. This is especially true for supermassive black holes at the centers of galaxies. When a supermassive black hole is feeding on its accretion disk, it doesn't just suck all the material in. The intense energy and pressure in the disk can launch colossal jets of superheated plasma. These jets are an outflow of energy, firing millions of light years out of the galaxy, perpendicular to the disk. This process, called AGN feedback, acts like a cosmic thermostat. These jets plow into the vast gas clouds within the galaxy, shocking and compressing them. This compression can trigger a massive new wave of star formation, creating billions of new stars. At other times, these powerful jets and radiation can blow the gas out of the galaxy entirely, halting star formation. In this way, the feeding habits of the central black hole directly regulate the life, death, and growth spurt of its entire host galaxy. Far from being a passive monster, the black hole is the active engine at the heart of the galaxy, shaping its evolution and seeding the next generation of stars and planets. Conclusion. From the one-way door of the event horizon to the baffling break of the singularity, black holes represent the ultimate frontier of human knowledge. They are not just cosmic oddities. They are fundamental to the structure of the universe. They are where our two greatest theories, relativity and quantum mechanics, go to battle. They warp time, forge new stars, and hold the answers to the deepest questions about space, time, and reality itself. They are the universe's ultimate magic trick, proving that the reality of the cosmos is far stranger, more complex, and more mind-bending than any fiction we could ever imagine. Further reading: Top 10 Enduring Aspects of Stephen Hawking's Life and Legacy. Top 10 Enduring Aspects of Stephen Hawking's Life and Legacy. The Threads of Reality. 10 Reasons String Theory Matters, even if you don't understand it. For those whose curiosity has been captured by these cosmic enigmas, here are a few accessible and brilliant books to continue your journey. 1. A Brief History of Time by Stephen Hawking. 2. Death by Black Hole and Other Cosmic Quandaries by Neil deGrasse Tyson. 3. Black Holes and Time Warps, Einstein's Outrageous Legacy by Kip S. Thorne. 4. Astrophysics for People in a Hurry by Neil deGrasse Tyson. Here at Zentara.blog, our mission is to take those tricky subjects and unlock them, making knowledge exciting and easy to grasp for everyone. But the adventure doesn't stop on this page. We're constantly exploring new frontiers and sharing discoveries across the digital universe. Want to dive deeper into more mind-bending top 10s and keep expanding your world? Come join us on our other platforms. We've got unique experiences waiting for you on each one. Get inspired by visual wonders and bite-sized facts. See the world through Zentara's eyes on Pinterest. Pin our fascinating facts and stunning visuals to your own boards. Discover quick insights and behind-the-scenes peeks. Hop over to Tumblr for snippets, quotes, and unique content you won't find anywhere else. It's a different flavor of discovery. Ready for deep dives you can listen to or watch? We're bringing our accessible approach to video and potentially audio. Subscribe to our YouTube channel and tune into future projects that make learning pop. Seeking even more knowledge in one place? We've compiled some of our most popular topic deep dives into fantastic ebooks. Find them on Amazon and keep the learning journey going anytime, anywhere. Connect with us and fellow knowledge seekers. Join the conversation on Blue Sky. We're sharing updates, thoughts, and maybe even asking you what wonders we should explore next. Perfect for learning on the move. We post multiple 10-minute podcasts per day on Spotify. Pop on your headphones and fill your day with fascinating facts while you're out and about. Follow us on Instagram for bite-sized knowledge. We post multiple posts per day on our official Instagram account. Every click helps us keep bringing honest, accessible knowledge to everyone. Thanks for exploring with us today. See you out there in the world of discovery.